Okay. In the preceding class, the preceding video, we're looking at the rules for exponents, and we're also looking at square roots. Okay. And we have, for example, square root of x to the sixth would be x cubed. Why? Because x cubed squared equals x to the sixth. And if that's a mystery, go back to the preceding video where we developed that idea. Okay. So square root is what you square to get the thing under the square root. What do you square to get x to the sixth? X cubed. Okay. And of course, by the rules of exponents, that means you're going to multiply this exponent by this to get the sixth. And we also talked about why x cubed squared equals x to the sixth. It's like x cubed squared equals, there's x cubed, and there's x cubed. Okay, we don't need now the parentheses in there. Just multiply them together, and of course that is x to the sixth. So we can always remind ourselves, even if it isn't x squared and x cubed, we can always remind ourselves of the fact that we multiply the exponents, because that has three x's, and we do it twice. Okay. Now, square root of x to the seventh. You could say that's x to the 3.5, and that would be right. Okay. So that equals x to 3.5. Since x to 3.5 squared does equal x to the 7. Okay. But that's not really what we want when we simplify this. I mean, sometimes we do work in decimal and fractional exponents. Okay, but we're not touching that here. Unfortunately, we should be able to do that, but we simply can't. So what we say is, okay, let's see. We've got the square root of x to the seventh. That's the same thing as the square root of x times x to the sixth, right? Because that's x to the 1 times x to the sixth. Okay. Or you can even say x to the 1 times x to the sixth, which is equal to the square root of x times the square root of x to the sixth, which equals square root of x times x cubed. In other words, we divide out the smallest power of x. It leaves us something that we can simplify by a square root. And then we would usually write that as x cubed times the square root of x. And you would want to do this, the last assignment in the course, to really understand this better. And it does it with numbers also. But now let's see what we do if we have a quadratic formula solution. Let's say you got x equals -3 plus or minus the square root of 36. No, we don't want 36. We'll do 72 over 2. Okay. Now what can we do with that square root of 72? Well, the first thing we can do is we can do the prime factorization of 72. Okay. And we find, we'll just jot that over here. I'm probably going to erase it. You know, you start with 72 and you divide it by the smallest possible number, which is 2. And that gives you 36. And you divide that by 2, and that gives you 18. And you divide that by 2, and that gives you 9. You divide that by 3, and that gives you 3. So that the square root of 72 is 2 cubed times 3 squared. Okay. Now, we understand prime factorizations. That goes back early in the semester. You might need to review one of the early assignments. And I'm talking more to some of the distance students who need to pull things together. And of course, everybody needs to pull things together. Because everybody here passed the midterm. Okay. Now don't slack off. You didn't pass it by all that much. Okay, if you didn't pass it by all that much, make sure you pass the final. But I think everybody here is in good shape that way. But I want to address some of the people who might not be here today, who are in this class, and distant students. So we want to make sure, and I'm just addressing this to anybody who's not here by virtue of being a distant student or being, of course, missing class today. You want to go back and review everything. And it kind of starts with fractions and things like prime factorizations and so forth. Makes it much easier to do this. So using prime factorizations, we could write that as the square root of 2 cubed times the square root of 3 squared. Okay. Well, using the same trick we did here, we can write it like this, can't we? Okay, 2 cubed is 2 times 2 squared. Let's write the exponent here, the minus of -1 times 2 squared. When we multiply, we can add the exponents. And also, I didn't do the step. Okay, I did a step like this, where I had like a 2 to the 1 times 2 squared instead of the x to the 1 and x to the 6. Okay. The square root of a product is the product of the square roots. Okay. So we can always do that. So I'll usually do that in one step after showing it initially. So we go directly from this to this because x times x to the 6 is x to the 7. So now what do we have? We've got -3 plus or minus the square root of 2 times 2 times 3. Because of course the square root of 2 squared is 2, the square root of 3 squared is 3. Okay. And of course 2 times 3 is 6, and we'll usually write the whole number or the integer out in front and then the square root next. Okay. It's not necessary, but among other things, that avoids confusing what's inside the square root and what's outside the square root. I wrote the 6 over here, and you wrote this line just a little longer. It might look like that 6 is under the square root sign. Okay, so there are plenty of reasons we want to put the integer out in front and then the square root. Okay. Well, having done that, of course, that would equal then -3/2 plus or minus 3 square root of 2. I think everybody is fully conversant with the quadratic formula, and we're going to review that anyhow. So if you're not sure how something like that could come about in the first place, you really want to review that quadratic formula assignment, because that's quite important. Okay. So anyhow, there we have an example. Does that help? Okay. Now, you don't necessarily have to go to the prime factorization if you can see what the biggest square is that you take out of that. Okay, so we could have written okay. Well, 4 goes into 72. So that's one square that we could do. We could write this as the square root of 4 times $18, okay? And that would be 2 times the square root of 18. But there's a square we can take out of 18, which is 9, okay? We get 2 square root of 9 times the square root of 2. Now, does that make sense? We simply factor out the biggest square we can. Now, we didn't factor out the biggest square we could because it took us 2 steps to get here. And sometimes it will. Sometimes you won't see what the biggest square is. Okay? But if you understand, of course, the square root of 72, well, let's just look at the squares. Okay, 2 squared is 4. 4 does go into 72, that's good. 3 squared is 9. Well, 9 goes into 72 8 times, right? Of course, now we know that 2 and 3 both go into 72, so we expect maybe that 2 times 3 goes into 72, which it does. But let's move on, pretending we didn't see that. Okay, the next square is 16. Well, 16, yeah, it goes into 72 4.5 times, but that's not going to help. Okay, and then that next square is a square of 5, which is 25. Now, 25 doesn't go into 72, no way, because if it ends in 5, it's got to go into something that ends in 5 or 0. Okay, those are simple arithmetic facts that not everybody is aware of sometimes. Okay, so and that makes it a little more difficult to visualize this. I think everybody here is good with those sort of things. Anyhow, okay, well, what's the next square? That'd be 6 squared, which is 36. And 36 goes into 72 twice. Okay, so we could write that as a square root of 36 times the square root of 2. So 72 is 36 times 2. And in one step, we get 6 square root of 2. So there are a lot of alternatives that you can use to reduce these things. You could start with the prime factorization. And if you've got a pretty big number in here, that's probably not a bad idea. Okay. If you got a number like 712 or something like that, instead of 72, you probably want to go to the prime factorization to make sure you've got every possibility. Okay. Now, if you know what the squares of all the numbers up to 20 are, then you'd be okay. But most people don't know that and aren't going to find the time to learn it. Okay, so again, prime factorization always works like this. Just dividing by the biggest square you can find that will divide into it works. And if you didn't really find the biggest square, if you thought 4 was the biggest square that goes into 72, when you looked at 18, you'd say, oh, wait, I can divide that by 3. Well, I can do that in another step. Okay. Most efficient is to know that 36 goes into 72 because you got to know squares. Okay. All right. So that answers the question as well as reviewing an important idea. Okay. Now we did pause for a second. Okay, at the end of the last class, the first part of the review, we reviewed the rules for exponents, and we developed and we talked about why x to the negative a has to be 1 over x to the a. And we talked about why x to the 0 should be 1. Okay. And if we assume x to the 0 equals 1, then we can prove that this has to always be true. But there are the rules. I'm not going to talk much more about them, except again to mention, just to emphasize, if you're doing x to the a to the b, that means x to the a is going to be that many x's. If x squared to the third power, you mean you're gonna have two x's here? And it's the third power, so you're gonna have three sets of two x's, which gives you two times three, or six x's. We need to understand that. That's something that I used a lot when I was learning, and I got very good mastery of algebra 2. I guess at the age of 15, which is typically when people take algebra 2. Even though I learned algebra 2 very well, I did very well on competitive tests, I did very well on the SAT. Okay. Got into a pretty tough school. When I was learning this, I think all through algebra 2, and even sometimes when I was taking a tough calculus course in college, I would check. I'd check this to make sure that I was using the right rule. Okay. I'd actually a lot of times write it out. So at your stage, you should probably, anytime you use this law or this law, write it out in terms of powers of 2 and 3. You'll retain it better, you remember it better, and on the exam especially, think to do that to make sure you don't screw up the rule of exponents. You'll probably be in the habit, and you'll probably be able to get them right, but use that little trick, that little insurance. Okay, and the rest of these rules are pretty easy to remember. This one seems a little weird. X to the negative 8 is 1 over x to the 8, but we showed last time why it has to be true. Okay, so let's just do a couple of examples. Let's say we got x cubed y to the 5th over z to the 4th raised to the 3rd power. Now, ordinarily in class, I'd ask you to work that out, see how you're doing and so forth, but we're trying to review everything. So we're not gonna take the time to do that, because in the first place, well, again, we have limited time. Second place, I think everybody pretty much knows. Okay. Okay, so this is what? Well, if we follow the rules of exponents, this is then there are two ways I can explain this. I'm making a decision and being kind of slow about it, but okay. I'm just going to cut to the y to the 5th cubed over z to the 4th cubed. I was going to give a little more involved explanation, and I'm sorry I delayed there to debate that with myself a little bit. But this is the way you're probably going to see it. Okay, see it most easily. So it's just, if you take the 3rd power of a bunch of products and quotients with no plus signs in there, okay, or minus signs, in other words, of one term, then you're going to distribute the cube over all the terms. So, and that doesn't officially show exactly why these rules lead to this rule. I guess there is one more rule that I should have written down. Since I started this, or I did, I don't really have room, but I'll write it anyway. I wrote the one for x over y to the a, but of course there's one for x times y to the a, just x to the a times y to the a, okay? That's just another rule. And I've used it here. I've kind of combined using this rule and this rule into one step. Okay, but again, it should be pretty obvious. It's like this power distributes over the multiplications and divisions, okay? So then x cubed to the 3rd is x to the 9. X to the 5th, y to the 5th to the 3rd is y to the 15th. C to the fourth to the third is C to the 12th. Now, one thing that I will ask, and that Open Math asks, there are two forms I could put this in. Okay. I could write this as x to the 9th, y to the 15th, z to the minus 12th. Does that make sense? Because, well, I could write this as x to the 9th, y to the 15th times 1 over z to the 12th. I could actually do that. We could say x to the 9th, y to the 15th over 1 times 1 over z to the 12th. Okay. And the 1 over z to the 12th is z to the negative 12th. So a positive exponent in the denominator can be written as a negative exponent in the numerator. Okay. And a negative exponent in the denominator will become a positive exponent in the numerator. The Open Math assignments covered that pretty well. You might want to review it. So let's look at one like this. X to the fourth, y to the negative third over z to the negative fifth squared. Okay. Now, first place, we can write that as x to the fourth squared, y to the negative third squared over z to the negative fifth squared. And that's going to equal x to the eighth, y to the negative sixth over z to the negative 10th. Because, of course, multiplying exponents. X to the fourth squared is x to the 4 times 2, which is 8. Y to the negative 3 squared is y to the negative 3 times 2, which is y to the negative 6, and so forth. Okay. Now, there are two ways we could write this. Okay. One way is like we have here. So that would be x to the eighth. Right here. X to the eighth over y to the sixth, z to the negative 10th, because the y to the negative sixth is, you know, again, we could isolate it just like we did over here. We could write x to the eighth over c to the negative 10th multiplied by y to the negative 6. Y to the negative 6 is 1 over y to the 6, and we end up with this. Does that make sense? I'm seeing dubious looks, so let me do it. I don't want to spend too much time on this because there are things we need to talk about, but this is one of the several important things. I found on the exam, just looking at everybody that took the exam, 7 or 8 people, it was hit or miss on the exponents. Okay. It was hit or miss on the distributive law. Some people did really well on distributive law stuff, expanding complicated expressions, and screwed up the exponents. Other people did the exponents just boom, 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 but couldn't expand x plus 2. Okay. So, and I'm not sure if that applies to anybody here because I don't remember specifically what you all missed, but I would say that the people who are actually sitting here in class did pretty well with that. Okay. Okay. Well, look, what does this mean? This means x to the eighth I'm going to do it in one additional step. Pretty soon I'll just stop thinking and just do what I'm doing. We're trying to make this as clear as possible, but it could be a little confusing. Okay, we can write this as x to the eighth times y to the negative 6 times 1 over z to the negative 10th, right? That makes sense? Is it clear that this represents this? If we multiply these out, we still get x to the 8th y to the negative 6th in the numerator, and we still get a z to the negative 10th in the denominator. All right. So that equals x to the 8th times 1 over y to the 6th times 1 over z to the 10th. Okay. So z to the negative 10th is reciprocal of z to the 10th. So that equals x to the 8th times 1 over y to the 6th times 1 divided by 1 divided by 1 over z to the 10th. Let me write that down here. One divided by 1 over z to the 10th, when you divide by a fraction, you multiply by its reciprocal. So that gives us z to the 10th. So 1 divided by the reciprocal of z to the 10th is 1 divided by the reciprocal of z to the 10th. Okay, which is 1 times the reciprocal of 1 over z to the 10th, which is z to the 10th. So we get x to the 8th, z to the 10th over y to the 6th. Now, this dividing by the reciprocal thing is why all this works. What you can see, once you understand this, is that a negative exponent in the denominator, whereas a negative exponent in the denominator flips up to the numerator, becomes a positive exponent. Okay? A negative exponent in the numerator flips and becomes a positive exponent in the denominator. So if we just compare these two expressions, hopefully everybody can read that. It should be clear on the video. So you're sitting back toward the end of this extremely large lecture hall. Might have a little trouble seeing that. But we see that the y to the negative 6th here ends up as a y to the 6th here. It just moves the y to the negative 6th to the denominator and changes the sign. And z to the negative 10th in the denominator moves to the numerator and the sign is changed. And here is the explanation of why. I'm not going to test you on the explanation of why, but should be able to do this. Now, what we've done is we've expanded this thing and we've expressed the result with no negative denominators. Okay? Now here, what we did was we took the third power of this expression and we got this expression, x to the 9th, y to the 15th over z to the 12th. This is the result expressed with no denominators. Okay? So now what that means is, whatever our result is, we take it and we flip everything in the denominator over to the numerator, but change the sign of the exponent. Okay? So that's exactly what we did here. Now, this is a perfectly good form. This is a form with no negative exponents. Okay. This form would be the result with no negative exponents. This is the result with no denominators. Sometimes you want this, sometimes you want this. Okay, so in this case, I expressed the result with no negative exponents. On some problems, you're asked to express the result in one form or the other. Might even ask to express it in both forms with no denominators and with no negative exponents, and identify which is which. Okay, and that's really pretty easy if you understand what we did here. It's pretty much all you need to know, but of course, if you run into problems with this, have more questions on it, email me or find me during office hours, okay? And we can clarify it. All right, does that give you what you need, you think? Okay, now I'm addressing everybody right now. I've posted on the assignments page for the DE60 course, copy of all the quizzes we've had. And I'm going to go through as many of those as I can right now in reverse order, starting with the most recent. Okay, the most recent was the 1125 quiz. Okay, so you see that toward the top of the assignments page. Note that you can also go to the assignments page and see the class for the 1125, which starts with this quiz. So if you don't understand what I'm telling you about the quiz, and don't understand what I'm telling you about, well, in this case, it's going to be function notation, you can work through that quiz as you would if you were in class. When I say, okay, now work this thing, now do this, now do that, to actually do it, okay? Now I'm talking more to distance students than I am to people who are here, but it could work well for anyone. Okay, so let's just say, the thing you have to understand about function notation, let's say f of x equals x squared minus 3x over 5x plus 2. Okay, and you want to find f of 3. The key is x is 3. When you write f of 3, you've replaced x by 3. So you replace all these x's by 3. And that gives you 3 squared minus 3 times 3 over 5 times 3 plus 2. And I'm not going to do the arithmetic because I'm just demonstrating what you need to know. Now, a couple other things I've asked. If you have like f of a plus b, x has been replaced by a plus b. So you replace this x by a plus b, you get the quantity a plus b squared minus 3 times the quantity a plus b divided by 5x, which would be 5 times a plus b plus 2. And then you simplify this. You expand this. You're going to get a squared plus 2ab plus b squared. You don't get a squared plus b squared. I emphasize that extensively in our last class. Okay? You don't get what it looks like you ought to get. It looks like that 2 squaring ought to distribute over addition. If that was a multiplication, it's kind of true because the laws of exponents would allow that. But laws of exponents don't allow you to distribute that 2 over the addition. It's not a multiplication, it's a power. So you got to write out a plus b times a plus b and use the distributive law correctly. Again, that was reviewed thoroughly last time, but I want to emphasize it because it's a really common error. Okay, that's all I'm going to say about the 1125 quiz. You should be able to go and do that quiz without any problem if you understand what I just said. And now I'm trying to find what I'm trying to find so I can quickly go to the 1118 quiz. What is happening here? Okay. Now, the 1118 quiz had a bunch of quadratic functions, or quadratic equations. Yeah, quadratic equations. Let's make sure we get the right dates on these. That's the 20th, sorry. Now, these aren't the problems that are actually on the quiz, talking about the rules you'd want to use. So you got a quadratic equation like x squared plus 5x plus 6 equals 0. You can use the quadratic formula. In this case, you can factor it. And this gives you x plus 3 times x plus 2 equals 0. So that x plus 3 equals 0, or x plus 2 equals 0. So that x equals -3, or x equals -2. Now, I wrote that fast. I'm not going to explain it. If you don't understand what I just said, go back and review what I said about that quiz on the video for the 1120 class. Okay. Now, another thing though, if it was x squared plus 5x plus 7, you use the quadratic formula. If you don't understand how to use a quadratic formula, go back and look at the video where I solve equations like this. There are 4 of them in the quiz. And or use some other online resource. Khan Academy is great. Quadratic equations. Open Math is some videos. Some are better than others. Most of them are pretty darn good. Okay. So you get here x equals -5 plus or minus 5 squared minus 4 times 1 times 7 over 2 times 1. And then you simplify that. Now, in this case, it turns out you're going to get square root of -3 here. That'll give you -3i. And if you don't understand that, I'm not going to keep saying it, but you should know, go back and look at what we did on the quiz, because we address it very specifically and very thoroughly. Okay, I think. Yeah, also, make sure you understand where this or comes from, why this means, and why x plus 3 has to equal 0. It's the 0 property of multiplication. If one thing is 0, the whole multiplication is 0. Okay, so the 1118 quiz is adding rational expressions. So I'm not going to write the word quiz for the sake of time. We've got 26 minutes left, so we should be able to get through a lot of these. Okay, so 1118 quiz. If we want to add these rational expressions, we do this. We find out the common denominator, which in this case is pretty simple. It's x minus 5 times x minus 3. In order to get that denominator, this expression, we can get the equivalent expression, the expression that's equal to this expression for all value of x if we multiply by x minus 3 over x minus 3. Now, we do have to write to the side that x minus 3 can't equal 0. We kind of already know that if we know that you can't divide by 0 here. X can't be negative 3, x can't be 3, because that would make the denominator 0 here, x can't be 5. So make sure you understand that. That's at rest, I think. So there we have this second one with the same denominator. Now the x minus 5 and x minus 3 are in different orders, but that makes no difference. If we were to multiply it out, we get x squared minus 8x plus 15 either way. Okay, so this denominator is identical to this one. So now we can add the numerators. We don't multiply these out at this point, and maybe we never do. If we just want our final result in factored form, which is usually the preferred form for analyzing a rational expression, then we do that. Okay, but this is simply, we find a common denominator, we multiply by some number over some number here, some number over some number here, exactly what we did in the first week of classes for numerical fractions. And we emphasize at that point, you better understand how to add numerical fractions and multiply and divide them, which is easier, okay? So that you can understand this. Well, then we can use the distributive law. Etc. Get the numerator. Keep the denominator x minus 5 times x minus 3. When you get this all multiplied out, then if possible, factor it and see if either of these is a factor of what you get, because then you can divide it out. Again, check out the video if you don't understand every word of what I just said. Okay. That's the 11-18 quiz now. I've got to keep looking back. I can't remember what all these are. The 11-13 quiz is finding least common multiples. And finding least common multiples, of course, is important for finding least common denominators. So let's say what there's common multiple of x squared plus 5x plus 6. And x squared plus 4x plus 2. We factor both of these things, we get x plus 2 times x plus 3. And we get x plus 2 times x plus 2. Except that should have been 4 there, not 2. Okay. Okay, so the least common multiple we just write down one of these or the other, because if it's going to be a multiple of this one, then it has to have an x plus 2 and an x plus 3 in it. Okay. Now we look over here and we see that we've got one of the x plus 2's, but we don't have the other one. We need two x plus 2's in order to have a multiple of this expression. So we multiply again by another x plus 2. And that's it. Okay. And when I did this, Keep an eye on the time to see just how much I can do. But when we did this, I kind of underlined this and said, well, there it is. Then I underlined this and said, well, it's there and there. We've got it. It's kind of split, but we've got it. Okay. So everything, and the least common multiple is the one that has just what we need for both of these and nothing more. If we wrote another x plus 2 on here, it would still be a multiple of both of these, but it wouldn't be the least common multiple. Okay. And let's see, the 11 quiz. You know, one irritating thing about this particular utility is it doesn't remember where it was. So you got to click on the document and then hit the page up. Okay, anyhow. Okay, now these quizzes should get easier as we go backwards. Okay, you can see how things are built, but I'm talking about the most recent stuff first because it's maybe more challenging than the rest of it. Okay. Okay, I want to multiply these. I can factor the numerator as x plus 3 times x plus 2. I can factor the denominator as x plus 4 times x plus 1. Over here, x plus 2 times x plus 2, which I could write as x plus 2 squared, but I'm going to keep it in linear factors. Okay. So factoring all these things, here's what I get. If I multiply these two, I'm going to get this. And you can do that yourself. It's pretty straightforward. I might make a mistake. So if I make a mistake, you know, just forgive me, but correct the mistake. You learn something that way. Okay. Now, I notice that I've got an x plus 3 up here and an x plus 3 down here, right? And x plus 3 is a factor of this whole numerator, and x plus 3 is a factor of this whole denominator. Okay. So I can cancel these, which just means that I kind of bring these x plus 3s out in front, and then I'll have x plus 3 over x plus 3, which is just 1. And another way to see it is x plus 3 divides into x plus 3 gives us 1. And 1 as a factor doesn't even have to be written down. Okay. Common factors of the numerator and denominator divide out. I don't like the word cancel because people do it wrong all the time. Be sure you understand what it means to cancel. It's a factor of the numerator, and factor of the denominator, okay? Like you can't divide this 4 by this 2. You can't cross those out and put a 2 down here. I've seen people do that. None of you. Okay, and I'm not sure, I don't remember what I saw on the midterm for the whole group. But there it is. Now, I could then expand all this. I could use the distributive law to multiply all this out and so forth. But I'm not going to take time to do that. Okay, so let's see. That's the 11th. That was the 13th. So this should be the 9th. But let me see if we've really got one for the 9th. Wait a minute. I had the 13th and 11th. No, should have been the 6th. Yeah. Okay. Here we're factoring expressions. That's 1106, not 1109. Factor like now let me make it easier to factor. Okay. Typically, we would have something like x to the 4th minus 5x cubed plus 6x to the 4th, x squared. Okay. Well, you can factor an x squared out of this. You're going to get x squared minus 5x plus 6. And now you can factor x squared minus 5x plus 6. And that's completely factored. Okay. So you always factor out the biggest term. Now there's another one that's a little more complicated. I recommend you take a look at it. The 1104 quiz is solving quadratic equations again. And I've already talked about that. So there are two quizzes separated by separated by 16 days. They do kind of the same thing. Yeah, they actually do the same thing. But there is one twist. Let's make sure we understand this. Here's a quadratic equation. Doesn't look like what you usually see as a quadratic equation. It has a square and so forth. But you know, if you multiply this out, you're going to get 10x squared here. Okay, you're going to get what, negative 60 and plus 10, negative 50x and negative 60. Okay. So that could be factored from that form, but it could just be given to you in this form. And what we're trying to get used to is zero property multiplication. This is going to be 0. 2x plus 4 is 0. Or 5x minus 15 equals 0. Okay, so you get two solutions. And of course, you can easily solve both of these equations. X is negative 2 or x is 3. Okay. Okay. That does it for November. Okay, let's go here. Okay, on the 1028 and the 1030, again, we're factoring expressions. So I'm not going to do that. It's just factoring and so forth. And we've already talked about it. You see that we kept talking about factoring for quite a while and what you get when you factor. Because one of the toughest things in precalculus is rational functions. It's stuff like this, okay? And graphing functions like this. And you develop the skills here that will make it much easier for you to learn that when you get to it in precalculus. Most students find that to be the hardest thing in precalculus. So we spent a lot of time on it. Okay. The 1021 quiz was scientific notation. This is an example of calculation in scientific notation. It equals 15 times 10 to the negative 17. 3 times 5 is 15. 10 to the 14th times 10 to the negative 31st. By the rules of exponents, is 10 to the negative 17. This is not in scientific notation. This number has to be between 1 and 10. It can't be 10, and it can't be 1, but any number in between. To make this into a number in between, I write it as 1.5 times 10, which is 1.5 times 10 to the first in this case. Okay. And then this equals 1.5 times 10 to the negative 16. Okay. Now, if you want to write out point zero zero, how many zeros there are? 6 zeros, 5 zeros, 5 zeros, 3, 2, and then 15 followed by 9 zeros. Okay. Well, you can multiply those out and try to keep track of the zeros, but it's much easier to write this as 3.2 times 10 to the negative 7 multiplied by 1.5 times 10 to the 10th. That's 3.2 times 1.5 times 10 to the third, which is 48,000. No, 4,800. And I'm not going to continue. Just look at the video if you need to understand this, but it's important stuff. Okay. The 1009 quiz. We have to go through the wash boards for the next class. Well, making me write too much. Okay. Make sure we're still recording. Um, two equations. Well, this is again, what I said the date was. Twenty-four, 1009. Okay. I'll number these equations 1 and 2. Equation 1, the x-intercept is at the point 10, 0. Y-intercept is at the point 0, 4. The x-intercept occurs when y equals 0. Y-intercept occurs when x equals 0. If you don't totally understand that, didn't understand that when you first looked at this, look at this equation. Look at the video. Okay. This means also these are linear graphs, these are straight line equations. So I put 10, 0 here. I'm going to put x equals 10 out here. And I'm going to put y equals 4 here. Here's the point 10, 0. Here's the point 0, 4. Equation 2, the x-intercept is, oh heck, I made that too easy. Might change my equation a little bit. Okay. I was going to get the same x-intercept for the second equation. We don't want that. Okay. Second equation, the x-intercept is, I did it again. Okay, I'm going to make it 5. Okay, the x-intercept now is 8, 0. Y-intercept is 0, negative 4. So I've got the point 8, 0. Well, if x is 10 here, x is 8, maybe about here. And y equals negative 4 would be down here. So there are my x and y intercepts for this equation. Each equation gives us the equation, it gives us a straight line. The graph of each equation is a straight line. Where the two straight lines intersect is the solution of the equation. The point is approximately equal to, well, if this is 8 and this is 10, this is less than halfway between 8 and 10. So I'm going to say it's about 7.6. And the y coordinate looks like it may be about 1. Okay. Now, if I plug 7.6 and 1 back into each of these equations, I should get something pretty close to 20 in this one and pretty close to 40 in this one. Well, you can plug those numbers in. 7.6 times 2 is 15.2, and 5 times 1 is 5, so we get 21.2. No, we get 20.2. I'm really good. Okay, just lucky. Okay, now if we plug this one in, I'm probably not going to be as lucky. Plug this one into this equation. I'm going to get 7.6 times 5, which is 38, minus 10 times 1, which is minus 10. So, you know, this estimate really sucks, the right equation. Okay, so I probably did something wrong when I did this. Because I don't get anywhere close to 40, I don't even get 30, I get like 28. I can't figure out what I did wrong, but I'm not going to take time right now. We've only got a couple of minutes left. Oh, we don't have any minutes left. Okay, well, this leads into solving two equations by elimination, which is something you also need to know. It's something that I believe would be addressed later on in this class. In a typical class, students work on the quiz, then we see how they did, and then we address difficulties. We talk about what we see that people tend to do wrong. I haven't talked about things that I didn't see anybody in here do wrong, but I often do see. Okay. And then we often develop that into something more. So if you're a distance student, haven't been viewing these videos as suggested strongly at the beginning of the course, start with this one. Okay. And good luck to everybody. A lot of people have done a lot of good work. And I hope as many people as possible passed. It looks like there's some who are unlikely to pass because they haven't done any work. Okay. Or they've done the work by maybe letting AI do the work for them, which means they probably aren't in real good shape here, but hopefully they can pull it out. We start with these videos, start with this review, okay? So good luck to everybody. I've enjoyed this class here. I've enjoyed working with the distance students. I hope you've been looking at my comments and your homework and trying to learn something from them. And many of you I know have. I'm open for questions all through final exam. Exam needs to be taken by the end of exam week, closing on Friday, I think at 5 o'clock. Okay. Be in the testing center. If you need to take a test at another testing center, let me know in advance so we can set that up. Okay, good luck to everybody, and I hope to see everybody in my pre-calculus class or somebody else's pre-calculus class before too much longer. Yeah, one final word. I can give you, I'm going to either give you a satisfactory or unsatisfactory in this course. Unsatisfactory means I don't think you're ready to go into an MDE 61 or an MDE 61 with pre-calculus. Okay. And it means, first of all, that you didn't do what it said in the syllabus. You didn't come out with a passing average. Okay. So I will still give you a recommendation, even if you end up not passing the course, it would be possible. I say, you're really smart. You just haven't done enough work. I think you could actually do this, but I still recommend you repeat this course. Okay. Another recommendation could be you might want to just take the MDE 61 without the pre-calculus because it's less pressure. You learn the same stuff. You just don't quite learn as much. And then you're ready to go into a pre-calculus course. Now that spreads it out a couple more semesters, but that is often the best route for somebody. Okay. I'll tell you what I think. It's not compelling. You can put yourself in any of these courses. Unfortunately, we're not allowed to placement test. Okay. And unfortunately, people put themselves in the wrong courses all the time. Take my advice for what you think it's worth, and then put yourself where you think you belong. Okay. I want everybody to succeed in pre-calculus. So do what's necessary to do that. I've enjoyed working with everybody. Stay in touch with me.